Okay, so this video, guys, I'm going to tackle going over review sheet number 1 and with a focus, though, on implicit differentiation there at the end because that was the most recent topic. So let's start to put some things together as we conclude this first half. So we want to find the derivative and simplify any answer with an asterisk. So again, that first question we ask ourselves is, do we have a quotient? And number 1, and the answer is no. Do we have a product? And the answer is yes. But would we use algebra first? Absolutely. So I'm going to take the pains to rewrite this as t. Well, when I multiply like bases, I have to add those exponents. So 2 plus 2/3, what's that? 6. 2 times 3 is 6 plus 2 is 8/3 minus 3t. And then that 1 plus 2/3, so t3, 2/3 plus 1 gives me there 5/3. And then finally plus t to the 2/3. So just remember now, all I did was distribute. I used algebra first. I'm then going to execute the basic power rule. So it's going to be 8/3 t, decreasing that by 1, subtract 3/3, and I'll get 5/3. Minus 3, drop down the power of 5/3, repeat the t, decrease that by 3/3, and that's going to give me 2/3 plus 2/3 t, and then when I take off 1, which is the same as subtracting minus 3/3, I will get negative 1/3. Okay, I'm just going to take those off there because originally that's not what was there. And obviously these 3's here divide out. And number 2, do we have a quotient? Yes. Would I do algebra first? No. I'm just going to do a quotient rule. So the quotient rule begins with the bottom, it's kind of slow, which is 4 minus 3x times the derivative of the top, which is 4x, minus the top times the derivative of the bottom, which is minus 3, all over the bottom squared. And this one here you'd have to clean up. So I'm going to distribute on top. 4 times 4x is 16x. And this times this is minus 12x squared. But this negative and that negative will make that a positive 3. And then when I distribute there, so I can see things right, I'll get 16x. And then this is 3x. Well, 3 times 2 is 6x squared. So 6x squared minus 12x squared is minus 6x squared. And man, if I see that at the end, it's positive 3 all over the bottom squared. So I just want to make sure there. 14x minus 12x squared, that looks good. That negative and the negative makes a positive 3, and that looks good right there. And I think I combined everything right. Okay. Number 3, do we have a quotient? No. Do we have a product? Yes. And I'd probably do a product rule. You could distribute in that one, but I think a product rule is kind of just as good. So it's going to be the first function, which is t squared plus t, times the derivative of the second, which is the function itself, e, times the derivative of the exponent, which is 2, plus the second, which is e to the 2t, times the derivative of the first, which is 2t plus 1. And although this does not have an asterisk with it, we're going to clean it up anyway. And factoring is the name of the game. So I'm going to factor out an e to the 2t. And what's left, very carefully, is 2 times t squared plus t, plus 2t plus 1, if I see things right. I'll distribute on the inside to get 2t squared plus 2t. And then just continue cleaning that up to give me 2t squared plus 4t plus 1. Again, just something very helpful to clean up. Factoring or getting a common denominator is how we clean up any derivative. And number 4, is it a quotient? No. Is it a product? No. But it is a function within a function within a function. So we are going to box the outside and circle that inside stuff. The derivative of sine is cosine. So I'm going to then repeat the inside. And this is where I'm going to kind of run out of room. Times it by the derivative of the inside. And the derivative of tangent is secant squared. Repeat the inside. And then times it by the derivative of this inside, which is e to the 3t, because that's the derivative of e, the function itself. Ooh, plus t squared, because I didn't see that was an exponent, times the derivative of the exponent, which is 3 plus 2t. And that does need to be in parentheses. In number 5, is it a quotient? No. Is it a product? No. But it's a function within a function. The outside this time is a cube. So I'm going to take that power to the outside. And how we differentiate a power function is by dropping down the 3, repeating the inside, decreasing the power by 1, and the derivative of sine is cosine. Repeat the inside and times it by the derivative of the inside, which is 2x. Okay, because the derivative of sine is cosine. Repeat the inside and then times it by the derivative of the inside. And number 6, what would be y prime? Well, it's not a quotient. It's not a product. It's a function within a function. And the outside function is ln. Its derivative is 1 over the inside times the derivative of the inside. Well, the derivative of cosine is minus sine. Repeat the inside. But the derivative of this inside is exponential now. So it is the function itself times the natural log of its base, which is 4, times 2x. Okay, that's the derivative of an exponential function. The function itself times the natural log of its base times the derivative of the exponent. And this negative sign over cosine could just give you a negative tangent of 4 to the x squared. It's okay like that. And now we're going to evaluate these limits by using derivatives because they are the definition of derivative. This first one is the limit as h going to 0. And in any definition of derivative, I need a function and an a value. My function, I'm going to try replacing, you can just, either one, it doesn't matter. I can replace this stuff with x. So I could see that my a value is 2 pi over 3, but my function is the sine of x. But now you have to complete it. The derivative of sine is cosine of x, but I need to evaluate that derivative at 2 pi over 3. So this becomes the cosine of 2 pi over 3. So the trig takes over. I'm going to graph 2/3 pi, which puts me here. My reference angle is pi over 3. Across from that's root 3, negative 1 and 2. Because remember, always across from pi over 3 is your root 3. The cosine is the x value, which is negative 1, while the r is 2. The next one is also the limit as h going to 0, but it's the x at f of x plus h. So my function here is this part, because it's f of x plus h minus f of x. So this is my function, and it's the ln of 2x squared minus 3x. The a value is just x because there is no indicative value. It's just in terms of x, like over here, it was 2/3 pi for a. So the derivative of ln is 1 over the inside times the derivative of the inside, which is 4x minus 3. And down here, this is the alternate form of the definition of derivative. It's the limit as x approaches a. So I need a function, and I know my a value is 2. In this form, the function goes first minus the f at a part. So the function is the natural log of x plus 3, and the a is 2 because when I sub in 2 for x, I get the natural log of 5. But I need to take the derivative of this function. And what is that derivative? 1 over the inside times derivative of the inside and x equals 2. So what's my answer? 1/5. And in number 10, what's the function and what's the value of a? This one here actually gets a little tricky. So it's not very easily to identify what a is because they did some kind of distribution here on this one. So here, because it can't be a 3h, to recognize the definition of derivative, it could only be plus an h, okay, in that form. And it's plus 3h. So if you take out a 3, you're left with 2 plus h then, minus, I'm going to make that e to that power, and that would be minus e to the 3x all over h. You're like, well, how did you get that? Because of the fact, if I let h go to 0, I would get e to the, well, I would get e to the 6 minus e to the 6, but I meant that if I distribute it back, I'd get 6 plus 3h, and then when x is 2, I would get e to the 6 power. So like when x is 2, I'd get e to the 6 power. And that's that portion right there. So this tells me that my function is e to the 3x. And the a value is 2. So once again, I just need a plus h here. I took out a 3. What's left is 2 plus h minus, now again, this here was 3 e to the 6. That might confuse you right there. So then what do I think is a good choice for my function? Replace the 2 plus h with x, and I think a good choice for my function is e to the 3x. Its derivative is the function itself times the derivative of the exponent. I need to evaluate that at 2. So I'm going to sub in the 2. That's e to the 6 times 3, and that's 3e to the 6th is that. Part 3. I need a tangent line for the graph of k at x equals 3. So please know this structure, that a tangent line triggers a slope, which is the derivative, but this derivative is k prime of x, and my a value is 3. So that's the same thing as x, though, guys. So it's just x is 3. So k prime, the derivative of the outside is f prime. Repeat the inside and times it by the derivative of the inside. I'm going to sub in the 3 for x, and then I'll get f prime of g at 3 times g prime at 3. Now I'm going to refer to the table to import my values. Starting on the inside, g at 3 is 6. So this becomes f prime at 6 because this value is 6 times g prime at 3. F prime at 6 is 5. And g prime at 3, if I could see things, is 2. And I'm getting an answer of 10. So f prime at 6 is 5. And g prime at 3 is 2. And 5 times 2 is 10. But now I need the output value for when x is 3. So k at 3 equals f of g at 3. What's g at 3 from the table? It is 6. And then f at 6 is equal to 4. So that y value is 4. But I still didn't write my line yet. So my line is I do it as y minus 4 over x minus 3 equals my slope. And cross multiply, and y minus 4 equals 10x minus 30. Add the 4 and get minus 26. So that was a function within a function derivative. The derivative of the outside, repeat the inside, times it by the derivative of the inside. And it's pretty cool, guys. Just sub in the value of 3 and pull the values from the table. Ooh, in part B, we only want h prime at 1, so there's no tangent line. So I'm going to do a quotient rule. So h prime of x is the bottom times the derivative of the top, which is g prime of x plus 2x, minus the top, which is g of x plus x squared, times the derivative of the bottom, which is f prime of x, all over the bottom what? Squared. And I'm just going to replace x with 1. I'm going to be a little lazy here And just now replace all of these x's, well, with 1. How's that going there for me? 1, and then 1, and then 1. I didn't want to write that all over again. Okay, so what is f at 1? Gotta obey the order of operations here. Just get a little tricky with the order of operations. So f at 1 is -6, and g prime at 1 is 2. But 2 times 1 is 2, minus g at 1 is 2, and 1 squared is 1, and f prime at 1 is 2. And what's f at 1 there? -6, I believe, squared. So hang in there. Let's do the order of operations. 2 times 2 is 4, times -6 is -24. 2 plus 1 is 3, times 2 is 6, and that's going to give me positive 36. So I'm getting -30 over 36, and I'm not worried about reducing it. So again, you had to do a quotient rule. Make sure this is in parentheses, like that. And hopefully I did everything all right there. Saw the table right. Is g at 1, if I can see things, is 2. Okay. This down here, is it a quotient? No. Is it a product? Yes. I'm not going to do algebra first. So j prime of x is the first, which is x squared, times the derivative of the second, which is g prime of x squared minus x, times the derivative of the inside, which is 2x minus 1, plus the second, which is g of x squared minus x, times the derivative of the first, which is 2x. I'm going to replace x with 2 this time, and 2 squared is 4. That's going to be 4 minus 2 is 2, and 2 times 2 is 4, minus 1 is 3. And then 2 squared is 4, minus 2 is 2, and 2 times 2 is 4. Be careful here, because this is g prime at 2. So g prime at 2 from a table is 0, guys. That's going to be pretty nice, because 0 times all that is 0. And g at 2 from the table is -3, times 4 is -12. Getting down there to the home stretch. What a great review sheet for the test. This one here, we're to do implicit. So I'm going to take the derivative of each side with respect to x, and every time I differentiate a y, I need to put dy dx, obeying all of my rules, of course. And the first part's going to need a product rule. So my first function is e to the y, and the second function is the sine of x. So it's e to the y, the first, times the derivative of the second, which is cosine of x, plus the second, which is sine, and the derivative of the first is e to the y, and the derivative of y is dy dx. So that's that whole first part. It's a product rule. Remember, never a derivative times a derivative. Equals, the derivative of x is just 1, and this is going to need a product rule. The first times the derivative of the second, which is dy dx, plus y times 1. And it really is easy, guys, because all we have to do is get the dy dx's to one side. But man, this whole thing is all multiplied by dy dx. So always put that at the end, because usually trails there at the end. You usually put e to the y first, but that's all right. And I'll take this over and minus x dy dx. And then that's going to be equal to, on the right side, y. That's going to stay, but this will come over and become its opposite sign. So I'm going to factor out the dy dx from the left side. And what's left is e to the y times sine of x minus x. So things are definitely getting a little longer, but very manageable because there's nothing there to combine. Then this is going to imply finally that dy dx equals y minus e to the y times cosine of x, all divided by your bottom, e to the y sine of x minus x. Okay? This is the part that I have to divide by. I think I did that okay. Down here, a good question for your exam is, I'm going to give you an equation and ask you to show me that the derivative ends up equaling this. So once again, we're going to do implicit. So for part A, the derivative of y squared is 2y dy dx, and the derivative of 2, a constant, is 0. The derivative of by a product rule is going to be x times the derivative of the second, which is y, which is dy dx, plus the second, which is y, times the derivative of the first, which is 1. I'm going to get my dy dx's to one side by subtracting that x dy dx over and keeping the y on the right. When I go to factor out the dy dx, it's going to be left 2y minus x equals y. I will then divide and get that dy dx equals y over 2y minus x, and done. In part B, we want to find all points on the curve where the line tangent to the curve has a slope of 1/2. So your tangent line is your derivative. It's the slope of the tangent line. So if I want the points where the curve equals a slope of 1/2, I'm just going to set dy dx, which is this expression here, equal to 1/2. That's all I'm going to do, is just set it equal to 1/2. But how do I solve that? Is by cross multiplying. So it's going to be 2y equals 2y minus x. And if I look here, guys, carefully, subtract the two y's and x is 0. And then if x is 0, I need to find y. What do I do with that? Put it back into the original. So it's going to become y squared equals 2 plus x is 0 times y. Well, that's just 0. And y equals plus or minus root 2 because that's into a square. So what are my points? 0 plus or minus root 2. And if I have, hopefully I have enough room there. In part C, finally, show that there are no points on the curve where the line tangent to the curve is horizontal. So we need to know, again, that vertical tangents imply where the derivative does not exist. And horizontal tangents imply where the derivative is going to be equal to 0. But in a fractional case, the derivative will only be equal to 0 when the numerator equals 0. And for that to happen, y would have to be equal to 0. But we're to show that if y has to be 0 to be horizontal, that no such points exist. So what do? Replace y with 0. And notice, does 0 equal 2? No. So therefore, no such points exist where the tangent line is going to be horizontal. And I just want to make sure here for part B, though, I kind of label that as an answer. And then we see there in part C that no such points exist here. So that's like part C. And the last part you'll have to do for your exam is to give an interpretation of the derivative in the context of a problem. So to do this, we have to use our calculator. We don't do this by hand. And I will bring up my emulator here. Okay, let's get that going. Okay, so now I'm gonna do second quit here. Why is that like that? Okay. And then where am I out here? Okay, that's here. Okay, so then you have to go here. So, okay, so then oh boy, let's see here. Let me go here and why isn't my emulator coming up here? Here it is here, but that's not what I want to be sharing here. So let me see. Hold on here. Okay, I think okay, there we go. So I'm going to go here. I want f prime at 7. And as a quick read through, f represents the rate. It's a rate function at which customers remove bananas from a display table. So f at t is the rate at which they remove bananas from the table, and f at t is measured in pounds per hour, while t is measured in hours. So I like going to y equals, I'm going to put my function in there, and it's going to become 10 plus 0.8x per times sine. Just do that, parentheses, x caret cubed divided by 100. Close it, enter. And then now I'm going to do second quit, math 8 for the derivative. And I'm going to put y1, alpha trace y1, and it's with respect to at the number 7. And I get for an answer negative 8.119, remember 3 decimal places. And finally now, what's my interpretation? So that's, we're going to use that template to interpret a derivative in context. We start with the template. At t equals 7 hours, the function, this is the function f. What is f? It tells you rate in the stem of the question. The rate at which customers remove bananas is decreasing, because this is negative, at a rate of 8.119. Don't say a double negative. And the units of a derivative are very clear. It's the units of f divided by the units of the input, which is t. What's f measured in? Pounds per hour per hour. And remember, we talked about this, that, we have different types of functions. We have rate functions and we have like an amount function. F does not represent the amount of bananas being removed. It represents the rate at which customers are removing the bananas. So therefore, this needs to read at t equals 7 hours, the rate at which customers are removing bananas is decreasing at a rate of 8.119 pounds per hour per hour. If F had represented the amount of bananas that the customers removed, then it would read at t equals 7 hours, the amount of bananas the customers removed is decreasing at a rate of pounds per hour. Okay, because F at t would have been measured in pounds with regards to time. And that closes that part out. And then just to spiral back quickly to some implicit problems here on the previous homework here. Number 20 is for a little bit of time here. I'm just running out of room. That's the only hard part, is how to insert a page here. So number 1, the derivative would be 3x squared and then a product rule, x times 2y dy dx plus y squared times 1 plus 4y cubed dy dx equals 0. And then the dy dx's are all on one side already. So I'm going to be a little quick here and just bring down my dy dx, but I'll explain where that comes from. I'm going to take this over and make this minus y squared. Take that over and make it minus 3x squared. And then I have a 2xy, which I would have factored out, plus a 4y cubed. It's hard, you don't have enough room there. Another one is number 2 as a product rule. So we have a product rule here. So this derivative would be x squared to be 2x. And this is my first function, minus 4x. times the derivative of the second, which is dy dx, plus the second, which is y, times the derivative of the first, which is minus 4, plus 2y dy dx equals 0, because the derivative of y squared is 2y dy dx. So then, the hardest part is I'm running out of room here. So I'm going to keep the dy dx's on one side. And let me see if I can borrow a little bit of room here. And just get rid of, oh, let's get rid of this right here. Okay, that's a little better. Frees up a little bit more room. And then this 2x comes over and becomes minus 2x. And that minus 4 goes over and becomes positive 4y. When I factor out the dy dx, I'll get that dy dx equals negative 2x plus 4y divided by negative 4x plus 2y. Number 3 is going to be another product rule involved here. So it's going to be 2x plus 2x times dy dx plus y times 2 plus 8y dy dx, which then equals 0. And then this one here, guys, the dy dx is already on one side. So this is going to come over and become minus 2y. And that 2x will become over, go over to the other side and become minus 2x. Factor out the dy dx, and what's left is 2x plus 8y. And then the last one down here is number 9, is to find a tangent line. Again, a tangent line triggers a slope, which is the derivative, and the point I already gave you is 2, 1. So what would that be? Well, it's going to be a product rule here. So this derivative is 2x right here. This is my first function, so it's not too hard to see. And that's my second. So it's going to be the first, which is minus x. The derivative of the second is dy dx plus y times the derivative of the first, which is minus 1. The derivative of minus x is just negative 1. And this derivative is minus 2y dy dx, which equals 0, because the derivative of 1 is just 0. Again, guys, the dy dx's class are already on one side, so just got to rewrite things like that. And I'll take over that 2x and make it minus, right? And then take that minus y over and make it plus. Once again, I'll factor out the dy dx, and there it is. And what is my actual slope at this point is found by replacing x with 2 and y with 1. So now when I do that, I'll get negative 4 plus 1, because x is 2 and y is 1. So negative 2 times 2 is minus 4 plus 1. That'll be minus 2. And then 1 times that's minus 2. So it looks like I'm getting here minus 3 over negative 4, which is 3/4. So my slope is 3/4. What's my setup of the line going to be? Y minus 1 over x minus 2 equals 3/4. And then you can cross multiply from there and get 4y minus 4 equals 3x minus 6, and then solve from there. Okay, and that highlights that. There are other good problems on this homework that we'll tackle, like this here is a product rule. But remember that the derivative of sine of y would be cosine of y times dy dx. Okay, but that is a really, really good review of what we need to know for this first exam coming up, which is, again, all your derivative rules right there, the definition of derivative, getting, the value of a derivative from a table, and then implicit, and then questions about implicit, and then finally, the interpretation of a derivative.